Welcome back. In this session, we'll continue our discussion about processing the messages from Kafka. In the last two sessions, we defined the problem statement. We divide the problem statement into multiple stages, and then we discuss about how to handle the message ingestion. So now in this session, we are going to talk about how do we process the data once it lands in the message Kafka. What are the design options what we have and what option we will choose for our use case. So now that we have successfully ingested the IoT sensor data into Kafka, the next stage is to process this data in real time. So to prepare for the anomaly detection. So, but before we dive into design option, just like we have asked the questions in the ingestion phase, even in the processing phase, we have to ask the questions. So first we need to ask the question is what transformations do we need? Do we need to clean the data? For example, we want to filter out the nulls, standardized temperature units. Maybe it is everything is in Fahrenheit. You want to convert centigrade, or maybe some remove some noise. Some this is essential to avoid something like we know that, right, garbage in garbage out when we hit the ML model. Second, we need to ask, do we need to enrich the data? Maybe the raw data doesn't have enough context. Maybe the date I'm getting, I may need to reformat it. Maybe you need to join the data. Maybe I need to have data from two sensors. I'm getting data from, say, temperature sensor, data from a vibration sensor, from a humidity sensor. I might want to join the data. Maybe I need to add, I'm getting the data, but I am having some master data which is another system. I might want to join this sensor data from the master data, right? Next, I need to understand what is my latency requirement. So am I looking for a sub-second real-time alerts, or I'm looking for a few seconds of delay, or maybe few minutes? Something is going to fail, I'm okay even if I inform that alert within a few minutes. Okay, so that affect whether we are using either micro batches or continuous streaming. So another key question is that we need to ask is, are we working with the, whether event time or ingestion time? What difference is that, whether the time the event has occurred versus the time the message actually landed in the your Kafka. Okay, the difference is that sometimes you need to work on basically the time where the event got generated, not the time when actually reading it, right? So next one we need to ask is, are we processing record one by one or in a window? So am I taking every sensor record and I'm processing, or I'm only taking the sensor values in the last 5 minutes or in the last 10 minutes? That means am using some windowing mechanism, whether it could be some tumbling window or a sliding window. Then we need to ask the question, which stream processing engine fits best for me? So do we have multiple things, like whether do you want to do something like a sparse structure streaming? We are going to talk more about that the next. And then can we use something like a Flink, or maybe we can use something like Amazon KDA, which is data analytics, or I might want to use something like glue streaming. So each has got a trade-off in latency, the developer experience, and maybe the integration with your existing tools. And next comes the most important key, right? You did all the processing, but you need to make some inference out of it. That's where we are going to invoke the ML model. How are we going to invoke the ML model? So are we going to deploy that in a SageMaker endpoint for production, or are we going to deploy it locally? Are we running some lightweight models? So a lot of considerations are there. Next, we need to think about how do we handle the processing failure. So what if one record throws an exception? You are processing a record. Do we retry? Do we skip it? Because I'm getting the stream of messages. Maybe one bad messages might not affect me, but I also want to make sure that that message could be critical message also, right? I want to make sure that I'm handling properly. And last question we need to ask, what does the output finally looks like? Should we flatten the message? Because I might be getting a JSON, I might want, but the model might not take a JSON. I might want to flatten the message, or maybe I'm getting a text message, but I want to convert into JSON, right? So these are the questions we need to ask. So once we have answered these questions, then we need to move on to exploring design options, because by now you have got a clear idea on what is your data processing requirement look like. Then you know that, hey, I have these data processing requirement. I cannot handle my data in micro batches. I want to handle in very near real time. Then maybe the Flink is the best option for me than a Spark streaming, right? So these questions will guide you in choosing your design options. Next, we will go through each and every design option and see like which design option is the best suitable for this use case. So before we go further, the way we have done in the previous stage to define the goal of the stage, right? So the goal of the stage is we are not just processing the data, we are also using that cleaned enriched stream to detect anomalies in real time using the machine learning model. So what does what does that basically it takes to do that? So basically we take the raw sensor data and perform necessary transformations or cleaning or maybe standardizing, and then we might enrich the data by joining this data with another master data or maybe some static references like device type or the location or maybe some threshold which is acceptable for this device. So this gives us a data context which is crucial for a actual inference of predictions. Then we apply an ML model in real time. This model might be as running inside Spark or Flink code, or it could be in a Amazon SageMaker, or we can call it through a REST API. So for every incoming message, we run an anomaly detection inference and attach prediction result like probability score. Whether is it going to fail, it is not going to fail, or maybe you could say there is a 90% chance of fail, or 50% chance of fail, and then all must happen in a low latency, because the whole idea is that we need to detect the risk of damage or downtime much before this will happen. So the end goal of the stage, now to rephrase it, is to turn a raw IoT event into real-time actionable insights, right? So, and also we should be able to store, visualize this data and also alert immediately. Next, let's understand some concept here before we dive into some of the options. One concept I want to talk about here is that Spark structured streaming. Okay, right? So what is Spark structured streaming? So Spark structured streaming is a stream processing engine built on top of Apache Spark. So what makes this is unique is that it treats stream of data as a continuously updating a table. So if you see traditional batch processing, right, basically what you do, you load data from a file or a table, process it once, and you are done with it. But with the Spark structure streaming, new data continuously arrives and Spark incrementally update the result as if the table is always growing and being evaluated or processed in real time. So let's walk through the visual below here, right? So if you see that on the left you see an input data, this could be coming from Kafka or IoT sensors or Kinesis. In our case we decide as a Kafka that enters a streaming query which is just written like a SQL query or data frame transformations in a Spark. So under the hood, what Spark is doing is it is actually, it has a long running query continuously processing a new data as it arrives. So the result of this query is in a in-memory table. Okay, that's why it is really fast, because it is in memory, which keeps updating the new records. And finally, this result table can be written into an output sink, which could be your S3 bucket, or it could be even another Kafka topic, or even any other storage mechanism which you choose. So the key takeaway is that Spark structure streaming is, let's just write streaming job like a batch jobs. That's the beauty of it. And Spark handles the complexity, like all the fault tolerance, the checkpointing, all the things it handles behind the scenes. So this makes us a really solid choice for a real-time data pipelines, especially when you want integrated machine learning logic or perform complex aggregations over a time window. So that brings us option number one for our use case, for the processing use case, which is a Spark structure streaming. So one good thing is that the why it is a great fit is it can work on any ecosystem you are familiar with. You could use Databricks, or you could use EMR on AWS, or you could run your own Spark cluster. So Spark can read data from Kafka natively and support streaming computation via either via micro batches, which is typically every 1 second. So that's 1 second is honestly is good enough for most real-time systems which you want, especially if you don't need a sub-millisecond latency. And for ML inference, we have two options. Either you can use preloaded lightweight model as a UDF, something like XGBoost or any scikit-learn models, or you can call a SageMaker endpoint or REST API per message and attach the prediction score. And Spark also provides, say, a native support for windowing. For example, if you want to see a rolling average, or you want to group the messages in a particular time frame instead of handling messages one by one, it provides you a native support for the windowing functions it provides. And most importantly, it handles a state, all the usual things like a checkpointing or fault tolerance really well behind the scenes. And it also integrate very cleanly with the S3 for storing all the enriched data, or maybe the storing results. And even if you are using another system like a Databricks, which can handles auto scaling on the monitoring, or maybe you want to do more like a notebook based development and deploy that into as a job in production, right? Or you can also use Amazon EMR if you prefer managing infrastructure yourself, or maybe you can also use Amazon EMR serverless also. So the trade-off is that the Spark is micro batching, but it is not, if you see, a true an event time stream processing. You think it is event time processing, but behind the scenes actually what doing is doing a micro batching. So if your use case requires a type of a millisecond detection, or maybe then Spark might be less ideal. It still can still work, but it might be less ideal. But for most of the cases where you have a scalable, a machine learning friendly, you want to have enterprise grade pipeline, Spark streaming is a really best choice. Now let's talk about another option, which is Apache Flink. Before we go and evaluate Apache Flink, let's understand what is Apache Flink, right? Apache Flink is basically a true real-time stream processing engine. So unlike Spark, which processes data in micro batches, Flink processes data one event at a time. So each sensor reading is processed immediately, no waiting for batches. So this allows us to detect anomalies the moment the spike occurs. So, and this also helps us to handle in a very low latency and also very fine-grained access control. And most important thing is that it has got built-in support for event time, so which is very useful in case of an IoT time. That means that is not about when we are processing, but when we are actually handling that, right? So something like with the watermarks, Flink can wait for the lay data intelligently and still compute the correct results. So something like a if as not a sensor goes offline and then sends you the reading 2 minutes late, so what Flink will do is still places it correctly in a 5 minute window. For example, at T1, T2, T3, T4, T5 having 5 time periods, and then the data at T2 is coming at T4. Using that watermark will help you to put the data in T2 correctly, even though the T2 data arrives in the T5, right? So that is the most critical part, important aspect of the Flink. And we can also something like track the why this helps us. We can track the rolling average of any sensor, like for example, you want to track rolling average temperatures per sensor over the last 10 readings, say. So now if new reading, this watermarking helps you to put the timelines properly in that window, right? So it also has got very good support for not only windowing and also joining, or maybe exactly once delivery. And good thing is it also very cleanly integrates with Amazon Kinesis Data Analytics, or KDA. or Flink on EMR, or maybe on Kubernetes. So for example, if you want to compute, say, every 5 minutes, you want to compute the max vibration, okay, and then you want to compare that to the what is the threshold level, which is already configured in another system as a master data. So you can actually join this IoT data with the static metadata, a table which is there somewhere else. And also you can add, then this also helps you to add, other than the joining something, like you also want to enrich the data using some type, or maybe the location where when this device has been maintained lastly, right? So that helps you. All this windowing mechanism joining helps you in these cases. And another important thing is that for any reasons, if a Flink crashes while it is processing a stream, it resumes from the last checkpoint without reprocessing already handled events, right? It failed, that's a checkpointing helps you. It failed at time t3, and then it came back at time t6. Then it'll start processing the messages from time t3 instead of again starting reprocessing all the messages, all the old messages. So in summary, so Flink is a purpose built for a low latency, high accuracy, event driven pipeline. So which is makes it for a strong candidate for most of the real-time streaming systems. The only thing is that there is a good amount of learning curve involved when you're dealing with the Flink. Now let's look at why Apache Flink is the best. What are some of the other? Maybe we talked all of them in the previous slide, but let's summarize them again here. Number one, Flink process one event at a time. So this gives us a millisecond level latency, which is critical when you're trying to catch the equipment failure in real time. Second, the Flink has got native support for event time and watermarks. This means if a sensor data, as I told, becomes late, say due to a network delay, Flink still places in the right time window, and our our ML model might not be the inference will be accurate, right? And the other important consideration is it is stateful nature of Flink. That means we can track metrics like a rolling temperature averages, or vibration deltas per sensor across events, and flag outliers intelligently. And other important feature is that we discussed in the last slide again, windowing logic. So I'm summarizing again. So whether we want to detect spike in last 1 minute sliding window, or we want to compute, say, per hour the summaries of each device. So Flink can do that natively with rich support for the windowing mechanism. And one of the best important feature of Flink is that exactly once delivery. That is especially important when you are calling an ML model or alerting a system. You don't want duplicate alerts every time there is a restart, right? Every time you have something, then you will be overwhelmed with alerts which are duplicate in nature. So that way you don't have too many duplicates in a processing system. So, and another important aspect is that AWS offers Flink as a fully managed service under the KDA, which is Kinesis Data Analytics, and you don't have to even manage all the infrastructure yourself. So to summarize, Flink gives us the latency, the accuracy, and also the most important thing is well integrated with AWS ecosystem, so that you don't have to you can run all these things without having to worry about managing all the infrastructure. Our next option in our design option is that AWS glue streaming jobs. So basically this is nothing but Spark structure streaming, but in a very serverless and AWS fashion. So you don't have to really worry about cluster management. So think of it like your Spark structure streaming and autopilot mode. So it can continuously read from Kafka, apply transformations like filtering, applying any threshold, or if you want enrich the metadata, and write the clean data to S3. So this is a great choice when your use case is more ETL focused rather than a low latency ML scoring. For instance, if you just want to process all IO data stream, flag anomalies based on threshold, and then dump both normal and all this and anomalies data into a different S3 bucket, the glue streaming works best for you. But other advantage is that it also integrates the glue catalog. So if you're having all the data landing up in S3 bucket, and then it makes easier if the glue you're using glue catalog, then you can easily query the data using the glue catalog. So even if you have something like Athena and all these things can actually use this data, you query data in glue data catalog. So, and most important thing, just like any AWS service, any serverless service, it is serverless. So you don't really worry about provisioning, scaling the Spark clusters, and AWS handles everything for you. You would just write a PySpark or maybe Scala code and deploy the job. So based on our use case for our industrial IoT, so we recommend using Apache Flink, via the KDA. So what is the reason? So number one, we need a real-time, per event analysis, not just batch scoring or transformations. So our sensor might send late arriving data. So we might need an event time processing with watermark to handle them correctly. And we want to compute the rolling averages or maybe rolling stats per device, get pattern like a sudden rise followed by some not no and some silence, something you're not getting data for sudden after sudden spikes, right? And which Flink handles very cleanly using stateful operators and complex event processing. So AWS offers this via fully managed service KDA. So we get enterprise grade features without managing any infrastructure. So glue streaming and Spark processing are great choice too, but they lean more towards ETL heavy and batch optimized use cases. For low latency, stateful, intelligent, IoT processing, Flink wins, pretty much hands down. Okay, that's one of the reason we have chosen Flink for our use case. Next, we'll evaluate our design options for the ML inference. So next, let's ask about what all the questions to ask in ML inference, right? In this stage, what is our focus? We are focusing on invoking the ML model to perform a real-time inference on the data we have processed and using the from the IoT devices. So there are several key questions that we need to ask, to make sure that the model invocation fits well within our pipeline. Should inference happen per record or in batches? This is crucial because a real-time inference per record will introduce a low latency but may be more expensive in terms of compute. Whereas batch inference might be cheaper but could lead to higher latency. So you might, if you are using some SageMaker endpoint, number of times whether you want to batch or you want to use the real-time inference. So the decision depends on the requirements, for response time and on the cost also. So next one is that what models are we calling and where it is hosted. So we need to determine whether your model is hosted. For instance, you might use something like Amazon SageMaker, deploy your model and use SageMaker real-time endpoint for serving inference. Alternatively, other platforms like AWS Lambda could be used for smaller, less resource intensive models. So understanding the deployment environment will help us to plan the integration and set up your calls accordingly. Next is that what is our latency and throughput expectations. When streaming data, we need to know the desired latency and throughput. Inferences, throughput we can expect. So this information will, why this information, this will basically help us to size the ML endpoint correctly and what instance to use for the endpoint, and maybe also configure the auto scaling for handling any spike and burst of data. So next question you need to ask is how will we are going to handle the model failures or timeouts. So model can sometimes fail and it can time out. So we need a plan to manage these failures. This could include maybe retrying failed invocation or maybe using a fallback model, okay, or a timeout handling mechanism. So we also need to alert the team the model failure occurs, repeatedly, right? Then we need to ask whether do we need versioning or maybe some type of A/B testing for the model. So as you improve the model, you will want to test different versions are strategies to find the best performing model. That's what a lot of people, right? They don't rely on one single model. They keep developing the models and then see which model actually best fits your use case. So, and also implementing version control allow us to make sure that we can easily roll back to the previous model if needed. And A/B testing allows us for a more a comparison in a very controlled environment between the different model versions, and which is the best choice of production. And next one is that the question in it ask is what input or output formats are required. The input data sent to the model and the output we can expect, right? For example, can model take a JSON, or it can take a CSV, or it can take a text, like what format required. So then based on that, your Apache Flink or the processing pipeline need to handle these formats and then convert them into accordingly before sending them to the model. And then next one is how do we track the inference metrics and outcomes. So after every model inference, we need to robust logging and metric system to track how well the model is performing. This might involve maybe something like CloudWatch metrics or latency, success rates, or even something like technically like a model drift if the model performance declines over time. So by answering all these questions, we can properly set up and monitor our ML inference process that will help us to efficiently, reliably, uh, invoke the ML model in real time with our IoT data. So in this slide, we explore the different ways we can invoke the ML model for real-time inference from our streaming engine such as Apache Flink, which we have chosen. So let's walk through each options quickly at high level and see what is the pros and cons of each option. So first we have Amazon SageMaker endpoint, real-time endpoint. So this is the most common option for production grade ML inferences. It is fully managed, supports auto scaling, low latency, and allows versioning and monitoring out of the box. You name it, it has got all the features. The trade-off is that it can be obviously slightly costlier, especially during periods of low traffic if you keep the endpoint always warm. But for our use case where inference is part of a real-time system, this offers a worthwhile trade-off. Second is AWS Lambda. You can use this for your model is very lightweight, say under maybe less than some 250 MB or 100 MB, and then you want to completely serverless setup. This Lambda is cost effective and simple, especially at low volumes. But the challenge is that you are constrained by the size, the execution time, and memory. And this may not be a best choice if you have a large ML model or a complex ML model. And third one is that SageMaker batch transform. So if you don't need a real time and are okay with delayed inference, this is also a great choice. But the great choice in terms of the cost, and it can handle large data sets and supports also model versioning. So, but in our use case, when we are trying to detect anomalies in real time, this acts some kind of a latency which is meant acceptable. Another option is a REST API invocation from a Flink. So you can host a model anywhere. So you build the model, you can host the model on your SageMaker or maybe on your EC2 or maybe on your ECS container or even outside AWS and call it via REST API. So this gives us the flexibility in terms of the cost and also, but it puts the burden on. But the only thing is that you have to manage all the timeouts, retries, error handling, and observability. And finally, maybe not so popular choice, but embedding the model inside the Flink using some techniques like format like a PMML or ONNX. So what is PMML means? It is basically a predictive model markup language. This is an actually XML based model for a lot of ML models. And then another one is that Open Natural Network Exchange, which is open format for deep learning and ML models. This is supported by both the PyTorch and TensorFlow and all this type of frameworks. Now let's look at our final recommendations. So after what are design options, we'll use Amazon SageMaker real-time endpoint for invoking the machine learning model. The reason being, the SageMaker provides a scalable and production-ready environment for hosting ML models. It supports auto scaling, version control. You can model the monitor model performance and also low latency. which are essential for our use case. Second, we are recommending to invoking the endpoint directly from Apache Flink. This the reason being we are keeping the processing logic and inference tightly coupled, so allowing us to apply the ML decision in line with the event stream. So since Flink is already performing event time windowing and transformations, integrating this inference here keeps the system clean and efficient. Third, we suggest using a JSON format for input output between Flink and the SageMaker. The reason being it is widely supported format, very lightweight format, and which is a more common thing, is easy for any developers also to code and build this. So, and finally, we have to have a monitoring and observability. For that we can leverage CloudWatch to track latency, errors, and invocation counts. So this allows us to set up alerts if the model fails or slows down, or maybe it is not working as expected in the production. So this gives us a production level reliability and insights. So now to summarize, this setup gives us all the best of all the worlds. We are having a real-time performance of Flink, the intelligence of trained ML model, and the scalability, and the low latency of SageMaker, all within the AWS ecosystem. So basically this design has got this also future proof for design. Even if you want to scale up and scale down, it's future proof, and it is also operationally robust.